All right, hey guys, this is a quick introduction to Bayesian methods. So we'll get this recorded for you guys. Once again, I want to extend my apologies to you guys. There was a major construction project that started this morning near where I live, and there was no warning. And so, uh, I'm sorry, put me way behind, and I ended up having to cancel. So once again, please accept my apologies. But let's do this. Let's do it. So guys, we are starting. This is an introduction to Bayesian methods. So Bayesian methods is really kind of like the statistical foundation, or almost kind of like the statistical godfather, if you will, um, of measures of clinical association, of diagnostic reasoning, diagnostic math, right? When attempting to kind of figure out, right, which test is the best test, which uh, set of clinical maneuvers, or which clinical maneuvers, which uh, diagnostic study is going to be the most appropriate, right? Based on accuracy, right? Based on some, based on specificity and sensitivity, all of those things, which we'll talk about in greater detail, right? But who is who is Curtis Bayes? So, or Sir Thomas Bayes, excuse me. Same person, by the way, that apparently also makes English muffins. Random fact. But so Sir Thomas Bayes was a theologian and a mathematician, right? And I have here that he lived over 1,000 years, but that's obviously not correct. He lived to be 60, born in the year 701 and died in, or 1701 rather, and died in 1761. He was not Gandalf the Grey, right? He was just Thomas Bayes, right? So Bayesian methods are essentially a type of statistics or type of statistical analysis that's used to solve for the likelihood of events, right, based on changing information, environments, and beliefs, right? Um, and so ultimately what we're trying to do when we use Bayesian analysis is we are trying to essentially um, determine probability based on changing information, right? Whereas, as we'll see in a minute, probability from a frequentist approach is fairly static. But with Bayesian methods, right, that can change, and we'll demonstrate that in a second. Okay, so Sir Thomas Bayes essentially created Bayes' theorem, and I have the equation for Bayes' theorem up here in the top right hand corner. But his theorem is chiefly concerned with probability, and probability is a branch of statistics that calculates the likelihood of occurrence of a phenomena based on chance. So let's use an easy example, right? Um, we use the easy example of a coin flip, right, or of a quarter. So we have two ways, okay? We have two ways um, that we could essentially examine the probability of getting heads when flipping a coin, right? So we have two approaches. We have the frequentist approach and the Bayesian approach. The frequentist approach will always express the probability in hard terms, like 50%, right? So a coin flip is either 50% chance of heads or 50% chance of tails, right? There's two sides to a coin, tails on one side, heads on one side. That's all you got, right? 50-50. But the Bayesian approach will essentially update the probability based on the number of actual occurrences. So let's say, for example, I do 4 coin flips. So my free so the so at first glance, prior to that first coin flip, I have a 50-50 shot. But with a Bayesian approach, let's say that I flip that coin 4 times, right? And 3 out of the 4 times the coin lands on heads, right? So I have a 75% probability of landing on heads as opposed to tails with a Bayesian approach, right? Uh, so the Bayesian approach might begin with a prior likelihood, for example, like maybe 50%, and then a resultant posterior, potentially subtracting or adding to that prior likelihood based on the number of occurrences, right? Um, So yeah, that really is the main gist, right, between a Bayesian and a frequentist approach. But let's kind of look at a graphical representation. So the same thing, right? So ultimately, we have a frequentist approach here. Obviously, the chances of a 50 of heads, uh, versus tails, right, is going to be 50%, right, from a frequentist perspective. But we can see with the Bayesian approach, after we have flipped that uh, after we have flipped that coin, right, 17 times, okay, we have essentially heads has occurred 5 times and tails has occurred 12 times, right? So if we take a look and we actually divide, I'm going to do this on my phone really fast. We divide 5 by 7, oops, wrong one. We divide 5 by 17. We're going to get approximately 29.4 or 30%. And if we look at the mean distribution, right, or the normal curve in this case, it's shifted way to the left, right? So the probability of heads here, at least after 17 coin flips, is approximately 29%, approximately 30% in this case. Okay, and we can see that as we continue, right, to uh, obviously continue to flip the coin, right, we will have obviously, um, you know, different odds as we continue to flip the coin, right? Until those odds obviously change over time, right? Okay, so why do we care? Like, why in the world do we care about Bayesian methods, right? Why does it even matter? Like, oh, okay, that's great that the probability changes over time. That's wonderful. But what does that mean practically? So generally speaking, right, we have our Bayesian factors that are used to express the likelihood of one ratio to another, right? So for all of you that go on further in your healthcare journey, whether you're doing AT, OT, PT, PA school, XPhys, whatever it is you're doing, right? You will likely end up at a certain point hearing about these terms, specificity and sensitivity, right? So obviously specificity, and we will define these later a little bit more in depth, but specificity is the likelihood of obtaining a true result in someone who is healthy and who does not have a disease or condition of interest. Whereas the sensitivity is essentially the ability of a test to determine the presence of a disease or condition, right, or be positive in someone who really does have the disease or condition of interest, right? And so we come up with different values for both specificity and sensitivity. And we'll talk, and I will will kind of parse out some specific examples of how this works over the next week and a half or so. Okay, so number one, this is the magic of the number one, right? So we're going to be getting into something that I kind of refer to as diagnostic math, right? And the one thing, if we can remember from a math perspective, that the number one essentially represents a probability of 100% accuracy. That this is going to really help us, excuse me, not only utilize Bayesian factors, but utilize things like specificity and sensitivity rather well, right? So one, that looks like the letter I, but it's actually one. Okay. One also represents obviously a known and presumably correct and perfect pretest probability. Okay, that the probability is true or accurate. We'll talk about how that works diagnostically. Many times when we are trying to determine the accuracy of a diagnostic test, um, generally, generally, um, we are doing so by comparing that to a gold standard, right? And or something that is known to be 100% accurate, right? As being a diagnostic criteria and or tool, right? So um, ultimately, the priors that we have, right? So based on what we know, okay, about the accuracy or reliability of a certain test, right? Either like the frequent and the frequentist perspective, like a coin flip, and or maybe we may express our own personal beliefs about specificity, sensitivity, or accuracy based on our own experience, what we know. Oftentimes in healthcare and or in like a research-based type of study, particularly within clinical trials, we typically express these uh, based on what is known from other studies, right? So this could be, right, described as incidence or prevalence, right, or pretest probability. We talked about that previously, right? So if we know the incidence of a certain injury, right, over a given period of time, that can be our prior and or uh, our known value, right? Same with our prevalence, right? And so we can actually utilize that known value as a prior, and then essentially utilize a Bayesian approach to predict an outcome based on number of occurrences, right? So for an example that we give here, right, is we know, let's say, for example, that we see a patient, like, so let's say we're a clinician, we see a patient with fever and a sore throat, and we are 60% sure that they probably have strep, right, prior to ever conducting a strep test. So based on experience, we can be highly certain that they likely have strep, right? And so we actually test the specificity or sensitivity of our examination findings uh, with the strep, right? All right. So guys, that was pretty fast, but that's a quick introduction to Bayesian methods. This is going to be the foundation for our discussion of measures of diagnostic accuracy as we move forward. So I will post this as soon as it uploads, but please give this a watch if you can, and I will see you guys Tuesday. Okay, take care. Much love.